Greetings everyone. We as a group, including Laksh Babel, Suryansh Ayush, and myself Abhijit Singh, are going to present you a presentation on experimenting with datasets for finding different properties using algorithms. So the dataset which we have chosen is Deezer social networks. So these are the table of contents. Okay. So in this presentation, we will find minimum spanning tree and shortest path using four algorithms, which is Prim's, Kruskal, Bellman-Ford, and Dijkstra's. These algorithms are essential tools for optimizing network connectivity and discovering efficient path spanning graphs. Also, we will do some mathematical operations which is like finding the average of minimum MST or shortest path minimum of minimum MST, etc., which are also significant for an efficient network connectivity. So we have taken two demos. Demo 1 is question 5th of midsem and demo 2 is the data set. So as mentioned in question 5th, this is the demo 1. These are the three graphs. You can have a look on it. We will discuss the output in the code. So let's get into these dataset. So this dataset is regarding friendship network, which is user-to-user connection, music-to-music connection, artist-to-artist connection, and genre preference from the users of three countries, which is Romania, Croatia, and Hungary. The friendship network are represented as graphs. So these are the four algorithms we'll discuss. So let's get into Prim's algorithm. So Prim's algorithm is a greedy algorithm which is used to find minimum spanning tree. So it starts with a single source vertex and gradually grows MST by selecting minimum possible connected, which is nearest to it. The resulting MST ensuring the connected tree with a minimum total width and can be used to optimize network connectivity and solve graph-related problems. So let's get into IDE to discuss further on. So this is the Prim MST code. So this is the public class Prim MST. Okay, this will run Prim MST in graph G from source vertex. This will scan vertex V. This will check about the cyclicity. This will check about spanning forest. Okay, so let's get into the main code. So we are assigning firstly someone variable of double data type, assigning it to 0. Then we are taking an array of double data type. Okay, so now in our dataset there are three graphs. So we are inputting the first graph in here. So okay, and then that values are assigning iteratively in someone variable, and after that we will assign that value into the array. Similarly for second graph and third graph. So after sorting, we'll get the average by this formula, the minimum by the 0th index, first index of the array will give median, and second index will give the maximum. So let's check the code output. Okay. So as you can see, this is the output, average, minimum, median, and maximum.
So, greetings everyone. My name is Suryansh and I'm going to discuss about the Kruskal's algorithm and Dijkstra's algorithm. Kruskal's algorithm is a greedy algorithm that finds the minimum spanning tree of a connected weighted graph. It adds the edges to the MST in ascending order of their weights, avoiding cycles to create a connected tree. The resulting MST is a connected tree with a minimum total weight, making it useful for optimizing network infrastructure and solving various optimization problems. Now we'll see the working of the Kruskal's algorithm on IntelliJ. Here, a double weight is declared, which is basically the weight of the MST. A Kruskal class is created in which the graph is passed one by one, as there are three graphs. Then the edges are sorted in the ascending order. Here is the code for running the greedy algorithm. Here is to check the total weight. This is to check whether there is a cycle or not in the graph, which is the most important step. And these are the helper codes which is called from the main function. Now in the main function, there is a sums2 array which is of double type. There is a sum variable which is also double type. And this graph is passed, graph G is passed, which is the first graph. Then a Kruskal MST class is called, in which the graph is passed. Then we'll calculate the MST weight of graph 1 and we'll pass the value in sum1, and after that we'll pass the sum1 value in sums2 array. Similarly, this is for graph 2 and this is for graph 3. And after that, the arrays is sorted so that the first value is minimum, second is median, and third is maximum. And for average, we will calculate the MST weight of all the individual graphs and divide it by 3. So now we will run the code. Yes. So here the three files are there, which is of data set in which there are three graphs. Zero is for source node. Here the output is there. Minimum is this, median is this, maximum is this, and average is this. Now we will discuss about the Dijkstra's algorithm. So Dijkstra's algorithm finds the shortest path between a single source vertex and all other vertices in a weighted graph. As we have assumed in this code, it iteratively selects the vertex with the smallest tentative distance and updates the distances of its neighboring vertices if a shortest path is found. The resulting algorithm guarantees finding the shortest path in graphs with non-negative edge weights and is commonly used in navigation systems, network routing, and pathfinding applications. Now we'll see the working of algorithm on IntelliJ. This is a Dijkstra's shortest path algorithm. Here, a double array is declared to store the distance between the two nodes. Directed edge array is declared to store the last edge on shortest source to vertices path. Index minimum priority queue, which is a double type, is created to store the priority queue of vertices. The code is basically to calculate the shortest path from one node to every other node in the graph. G is the edge vector diagraph and S is the source vertex. This is a Dijkstra. This is the Dijkstra spirit, which is a public to and in which the graph is and the source node is passed. And these all are the helper nodes. This is for relaxing helper classes, which will be called from the main function. So this is the main function. We have created a variable of someone, which is a double type, an array of double type. This is the G is the stands for the graph one, and S is the source node. And then we will call the Dijkstra shortest path by passing the graph in the source node. And after that, the vertices are iterated, and the shortest path between every two nodes are stored in sum1. And after that, the sum1 value is stored in array. Similarly, this is for graph 2 and this is for graph 3. Again, the array is sorted to find the minimum, maximum, and median value, and average is calculated in a similar way by calculating all the sums, by summing all the sums and dividing by 3. Now we will run the code to see the output. So here is the median, maximum, minimum, and average of the as the output of demo 2. Now I would like to call my friend Laksh to continue.
Greetings to everyone. I am Lakshya Vavel, and now we are going to look upon the Bellman-Ford algorithm. The Bellman-Ford algorithm is used to find the shortest path from a single source vertex to all the other vertices in the weighted graph, even when negative weight edges are present. It iteratively relaxes the edges, updating the distances of the vertices by considering all the possible paths for v minus 1 iterations, where v is the number of vertices. The algorithm can also detect negative weight cycle by performing an additional iteration, identifying situations where distance update occur during the iteration. Now we are going to look upon the working of the algorithm in the IntelliJ. So this is the algorithm of the Bellman-Ford in the IntelliJ. First, we will initialize the double array, then the array of the S2, the Boolean array, and the Q. In the double array, we will store the distance of shortest path from one vertex to another vertex. Then in the S2 array, we will store the last edge on shortest path. In Q, we will find whether the V is or the vertex is currently on the same queue or not. In the queue, we will store vertices that we want to relax. These are some helper classes that will be called from the main function of the code. So this is the main function. First, we will initialize the sums array with the data type of double, in which we will store all the output from the that we have inputted in the code of the graphs. Here we will input the edges. Then in the Bellman-Ford SP, this is the public class in which we will pass the graph and the source node from which we want to find the shortest path to other vertices. In this if condition, we will check whether the negative cycle is present in the data set or not. If the negative cycle is not present, then this for loop will iterate through the each and every vertices of the graph. Then the output will be stored as the sum1, which will be stored in the array of the sums. Similarly, we will do with the graph second and the graph third, like this. Now here we will find the average of the sum1 plus sum2 plus sum3 divided by 3. Then we will sort the sums array for finding the median, minimum, and maximum of all of the shortest path from all the three graphs. Then we will see how to run this code. We will go for edit configuration.
Here, these are the input files, file 1, file 2, file 3, and the 0 represent the source nodes. Now we will run this code. So these are the output of the code, average, median, minimum, and maximum. Now we are going to look upon the presentation for further classification and the further description. The code that we have run for demo 2, similarly we will do in demo 1 to find the results. These are the following results of the demo 1. And these are the results of the demo 2 that we have, how we run the code, and the output of the code, the output of the dataset are these. So with the results of the demo 2, I would like to end this presentation, and thank you everyone for your attention.